Hello friends, how do you determine the relative acidity of protons? So that is our topic for discussion today. So we have seen in the Bronsted-Lowry concept of acids and bases, it is based on the protons. Acid, it is a proton donor and base is a proton acceptor, you know that. So acid-base reaction, it is a proton transfer reaction. That is here a typical acid HA reacting with a base B. So we are getting a conjugate base and a conjugate acid. Okay, now a loss of a proton from the acid results in the formation of the conjugate base, you know that. Okay, now strong acids that they have weak conjugate bases. Okay, so weak bases, they are very stable species because they do not readily want to share their electron pair to form bond with a proton here. Correct. Now strong bases, they want to share their electron pairs to form bonds with the protons there. So anything that stabilizes the conjugate base A, it will make the starting acid HA more acidic. That is the acidity of the acid. It is determined by the stability of the conjugate base. That is, the more stable the conjugate base, it means the more weaker. That is the weaker acids. Correct. It will not favor the reverse reaction here. In an equilibrium reaction, the forward reaction is favored only when the conjugate base is a weak base here. Okay, the strong bases, they want to share their electrons to form bonds with the protons there. Therefore, a weak base, anything that stabilizes, that means the conjugate base should be a weak base here. The electron pair should not be readily available to form bond with a proton there. Therefore, anything that stabilizes the conjugate base A makes the starting acid HA more acidic here. Okay. Now, the more stable the conjugate base, the equilibrium, it will be shifted towards that conjugate base because the forward reaction in equilibrium, the formation of the weaker acid and the weaker base is always favored here. Okay, now the structural differences between the molecules, okay, it can profoundly affect the acidity here. That is acidity of the protons here. Okay, now we have seen that one of the most important factors determining the acidity of HA, it is the position of A in the periodic table. Correct? That is identity. Identity of the element is most important thing here. Okay, now when we see the periodic table here across a row or the periodic table, the acidity of HA, it increases as the electronegativity of the element A increases here. Okay, now across a row of the periodic table, acidity increases. Okay, from left to right. Correct. So the stability of the conjugate base is the most important thing here. Okay, now stability of the conjugate base means, let us examine which are the factors responsible for that, because we have seen inductive effects. In the last class, we have discussed the inductive effect. A compound, say this CF3, CH2, OH. So it is a stronger acid compared to CH3, CH2, OH. Because of the presence of the fluorine atoms here, electronegative fluorine atoms here. This is the inductive effect. Inductive effect means the pull of electron density across a sigma bond. Along a sigma bond, that is pull of electron density along a sigma bond, it is on account of the difference in the electronegativities of the atoms there. Okay, because of the difference in the electronegativity, that is why this electron density is pulled. Correct? That is electron withdrawing inductive effect and electron supplying, that is donating inductive effect. We can see plus I effect and minus I effect we have seen there. Therefore, the acidity of HA, it increases with the presence of electron withdrawing groups here in A. Correct. Now, and there are other important factors responsible for the acidity of the protons. That is the acidity of the acid HA. It will be influenced, rather affected by other factors like resonance stabilization of the conjugate base and the hybridization of the conjugate base here. There are two aspects which we are going to discuss now. One is the hybridization of the conjugate base A, and as well as the stabilization, resonance stabilization of the conjugate base A here. Now, the most common HA bonds here. Now, first we should identify the atoms bonded to the hydrogen atoms here. Okay, and then we have to see the periodic trends to see the relative acidity. That is one method we have to adopt. That is, identify the atoms that is bonded to the hydrogen atoms here and use the periodic trends. That is, we have seen the periodic trends. Okay, now the most common HA bonds here, HA bonds, the most common HA bonds in organic compounds, they are carbon-hydrogen bonds. Then we have carbon-hydrogen bonds. Then we have nitrogen-hydrogen bonds. Then we have oxygen-hydrogen bonds. These are the most common bonds here. Okay. Now, acidity we have seen, it increases across a row of the periodic table. That is from left to right here. The relative acidity of these compounds, of these bonds, it will be the CH bond. It is the least acidic one. Okay. So, CH is least acidic. Then your NH. Then comes OH. That means the most acidic bond here, it is the OH bond. That is a hydrogen atom bonded to a heteroatom here. Carbon-hydrogen bond is the nitrogen-hydrogen bond and oxygen-hydrogen bond. So, hydrogen bonded to heteroatoms. Okay, that will be more acidic here. CH bonds usually less acidic compared to the hydrogen atoms bonded to the heteroatoms here. Okay, so now if two hydrogen atoms, they are bonded to the same element, how would you do that? Then you have to see the conjugate base. Draw the conjugate bases. Then you have to look for other points of difference here. Okay, other points of difference means the main thing which you have to see is whether there are any electron withdrawing groups. Okay, which will stabilize the conjugate base, because most important point here is the stability of the conjugate base here. Okay, therefore we have to see differences here. Points of difference we will have to identify. Most important thing, do whether there are any electron withdrawing groups here which will stabilize the conjugate base here. And another point we have to see whether the conjugate base, it is resonance stabilized. That is, resonance stabilization means it is electron de-localization. Correct. So what is meant by resonance here? That means we have seen resonance means the structures of certain molecules cannot adequately be represented by a single Lewis structure there. So sometimes we may need 2 or 3 Lewis structures, valid Lewis structures we will have to draw. And neither of the Lewis structure it will be representing the correct characteristic. Mean it will not be accurately representing that particular molecule. Okay, it will be a hybrid. That means a combination of the various structures. That is resonance structures we call it. Okay, now resonance structures means there will be difference in the location or rather position of the electrons there. Which electrons? Electrons either non-bonding pair of electrons or lone pair of electrons, and electrons in a pi bond. Okay, there will be a difference here. Difference in the location in resonance structures. The most important thing is there will be difference in the location of either the non-bonding electrons or lone pair of electrons or the electrons in the pi bond, as well as the pi bond itself here. That is, atoms, the position of atoms, there is no difference. Okay, the position of the electrons, pi bond, that is a double bond or a triple bond, that is multiple bond. That is what we call pi bond here. Okay, the difference in the pi bond and the difference in the non-bonding pair of electrons. That is the resonance structure here. So, we have to see whether the conjugate base, it is stabilized on account of resonance. So, resonance means electron de-localization we can say. De-localization of the electron density. Because of that thing, the conjugate base gets stabilized here. Because the electron density is not concentrated, rather localized on a particular atom. It is delocalized. It is getting spread over 2-3 different atoms here. Therefore, it is getting, electron density is getting diluted. When it is getting diluted, the conjugate base becomes weaker. It is no longer able to form bonds with a proton. The electrons are not available to form bonds with the protons there. Correct. That is how we will have to examine the points here. Now, in the case of hybridization, hybridization effects means that is the conjugate base we will have to see. That is the acidity HA of the acid, it is getting affected by the hybridization of A. Okay, now hybridization of the conjugate base. Okay, because of the hybridization, the conjugate base is getting stabilized. Correct. Now, let us examine this issue with the help of, say, alkanes, that is hydrocarbons here, that is 3 different compounds containing a carbon-hydrogen bond. We can examine here. One is alkane, a compound alkane. An example is ethane. Okay, here the carbon atom is sp3 hybridized, correct? Then we have alkene. Alkene, an example is ethylene. It is sp2 hybridized carbon here. Then we have alkyne. Alkyne is acetylene. It is sp hybridized carbon here. Okay, now see, these are the fundamental things here. Alkanes, alkenes, and alkynes, they all differ in their acid strength here. See, alkanes, the pKa value, it is in the range of around 50. So in the case of alkene, the pKa value is in the range of 40. So alkynes, it is around 25. So from these pKa values, we can understand that alkyne or acetylene, we can say alkane, alkene, alkyne. The alkynes have got the lowest pKa value here. When lowest pKa value means stronger acid. Correct? Therefore, alkyne, or we can say acetylene, it is a stronger acid compared to ethylene and ethane here. Correct? Acetylene is a stronger acid because the pKa is 25 and pKa of ethylene is 40 and that of ethane is 50. Therefore, the lower the pKa value, the stronger the acid. Therefore, acetylene is a stronger acid in comparison with alkenes, that is ethylene and ethane here. Okay, so now why? Now let us see the conjugate bases here. Correct? Now we have to see the stability of the conjugate base. Now why this alkyne, the acetylene, is a stronger acid compared to the other two hydrocarbon compounds here. Okay, now let us see the stability of the conjugate bases. The conjugate base means, so loss of a proton results in the formation of a conjugate base here. So this is the conjugate base of ethane, correct? This is a negatively charged carbon here. Therefore, this is a carbanion. Okay, that is a carbanion. So in the case of ethylene, we get another carbanion here. Then in the case of acetylene, we get the acetylide anion. This is acetylide anion. This is alkyd anion. Therefore, now these are the 3 conjugate bases here. Now we'll have to see the hybridization of the conjugate base. That is the hybridization of the negatively charged carbon atom. We have seen here in the case of alkane, here the carbon is sp3 hybridized and here it is sp2 hybridized. Here it is sp hybridized. Now we have to identify another important characteristic here. What is the percent S character? Percent S character. That means in the hybrid orbital, what is the percentage of the S orbital here? That is sp3. That is, we have 1 s orbital and 3 p orbitals here. Okay, now total 4 orbitals. Out of the 4 orbitals, only 1 s orbital is there. Therefore, the percent S character here, it will be 25%. And here it will be 33%. Then here it will be 50%. sp, that is 1 s orbital and 1 p orbital. That is 50-50 here. Okay, therefore the percent S character, it is. Now let us examine the nature of these electrons here in the orbital here, s orbital here we can see. Okay, now we have seen the alkynes here, they are more acidic compared to alkane and alkene here. Okay, now the carbon atom is, in the case of alkane, it is sp3 hybridized, we know. Now the electrons in a 2s orbital, okay, of an unhybridized carbon atom, we can say, so they are held very close to the nucleus here. The electrons in the 2s orbital of an unhybridized carbon atom are held closer to the nucleus in comparison to the electrons in a 2p orbital. That is 2s orbital, 2p orbital. Electrons in 2s, electrons in 2p. 2s orbitals are lower energy. Okay, the electrons are held close to the nucleus there, compared to the 2p orbitals here. Therefore, the closer the electrons to the nucleus, what happens here? The more tightly they are held. And therefore, these 2s electrons, they are not readily available for forming bonds with a proton. Okay, that is why they have become stable. That is the stability because of this thing, electrons in the 2s orbital, which are held very close to the nucleus, they are not readily available for forming bonds with a proton. Therefore, the conjugate base here. Okay, the sp hybridized conjugate base, that is the acetylide anion. It is a weaker one. Acetylide anion here, because sp orbital here, it has got more s character. 50% s character is there than an sp2. sp2 33% s character, and an sp it is 50-50 here. sp is 50-50, sp2 33, and sp3 it is 25% here. Okay, now here we can see the acetylide anion, the electrons in the sp orbital of a acetylide anion. See, or in the case we can write here in like this also instead of s. Okay, this acetylide anion, they are held more tightly. Okay, then are the electrons in a sp3 orbital of an alkyl anion here. Correct. Now, the acetylide anions are therefore weaker bases. Correct. Because why they are weaker bases than the alkyl anions? Because their electrons are not readily available. Okay, they don't want to share their electrons with the protons readily, as in the case of an sp3 hybridized carbon atom here, electrons here. Correct. So weak bases, they have strong conjugate acids. Weak bases, they have strong conjugate acids. Therefore, the acetylide anion, which is a weak base, correct, it has got a strong conjugate acid, acetylene. Therefore, acetylene is a stronger acid here. Okay, alkynes are stronger acid than are alkenes and alkanes. Okay, compared to alkanes and alkenes, alkynes are stronger acid here because the acetylide base, it is a weak base. Correct. Acetylide anions are weaker bases than are the alkyl anions here. Since the acetylide anions, they don't want to share their electrons readily with a proton. Correct. That is the reason. Now, the higher percent s character means what? That is, the hybrid orbital has a larger fraction of the lower energy s orbital. Correct. The percent s character, we say a higher percent s character means that here, in the case of acetylide anion, the percent s character is 50% here. Okay. Now, the higher percent s character, it means the hybrid orbital, it has got a larger fraction of the lower energy s orbital here. Okay. Now, the higher the percentage of s character of the hybrid orbital, the more stable the conjugate base is here. Okay. Therefore, acidity increases. Now, again, you see, we are concerned with the acidity factor, that is the proton. Acidity of the relative acidity of the protons here. Now, the acidity of the acid increases here. Acidity increases as we go from ethane to ethylene to acetylene here. Because the negative charge on the conjugate base, it is stabilized by increasing percent s character. Okay, it is a general thing. General principle here. Okay, therefore, acidity of HA, it increases as the percentage S character of A increases here. Okay, this is the point about acidity factor here. Now, let us examine the resonance. So, acidity and resonance, how they are interrelated. Let us briefly examine. So, resonance, we know, different Lewis structures, the position of the electron different here. Okay, resonance and acidity. Okay, now let us see the resonance stabilization here. Okay, it accounts for, see, we have seen the carboxylic acid. Carboxylic acids are more acidic than alcohols here. Now these phenols are more acidic than alcohols. Correct. There are so many phenomena like this which is to be explained in terms of resonance stabilization, we can say. It accounts for why carboxylic acids carboxylic acids are more acidic than other compounds containing a OH group. Other compounds containing a OH group means this alcohol is there. Then we have phenol. Okay, all these compounds are there. Now we have to compare why it is happening. Why carboxylic acids are more acidic compared to alcohols here. So now the most important point here is, so we'll have to see the conjugate bases here, the stability of the conjugate base. Okay, now if the conjugate base is stabilized, resonance stabilized, correct, then the starting acid, it will be a stronger acid. If there is a resonance stabilization, that means the conjugate base is, if it is stabilized, resonance stabilized, correct, it will become a weaker conjugate base. Once the conjugate base is a weaker one, the starting acid will be a stronger one. Correct. Now let us examine in the case of acetic acid. Okay, so we will examine 2-3 compounds like this here, and let us see the relative acidity of the protons here. This is acetic acid. Now acetic acid is pKa, it is around 4.8. Then we have your ethanol, CH3, CH2OH. Okay, the pKa is 16. Therefore, from here we can understand the lower the pKa, the stronger the acid. Therefore, acetic acid is a stronger acid compared to ethanol here. Correct. So, how will you explain this phenomena here? Now we have to draw the conjugate base. That is how we have to proceed. Okay, now let us see the conjugate base of ethanol, how it looks like. That is, we have CH3, CH2OH. Okay, the loss of a proton, it will give you the conjugate base here. That is, we are getting ethoxide anion. This is the conjugate base. This is ethoxide. Ethoxide anion is ethanol. Ethanol is the acid, pKa 16. Okay, so this loss of a proton is giving a conjugate base ethoxide here. Now, in the case of ethoxide here, there is no resonance here, because we cannot draw more than one Lewis structure. Correct. Only one Lewis structure can be drawn in the case of a ethoxide here. Okay, because the negative charge in the case of ethoxide, it is localized on the oxygen atom here. Okay, that is negative charge, it is concentrated only on that oxygen atom. There is no way out here further for de-localization or spreading of that negative charge here. It is localized here. But in the case of acetate anion, that is acetic acid, CH3, this is our acetic acid here. So acetic acid, which is the conjugate base here, the conjugate base will be CH3, CO minus. Correct. So this is the conjugate base of, that is the acetate anion. Acetate, that is a carboxylate anion, because acetic acid is a carboxylic acid. Therefore, this conjugate base is carboxylate anion, or we can say acetic acid, acetate anion here. Correct. In the case of acetate anion, we can draw two resonance structures here. Two resonance structures are possible here. This is one resonance structure. Then there will be electron delocalization here. How this electron delocalization? This. Okay. Now, here there will be two electron pairs. Okay. This is the acetate anion here. So, electron delocalization takes place in this fashion here. Okay. Now, which will be the next resonance structure? Let us draw the next resonance structure. And the resonance hybrid. This is the second resonance structure. Okay, so in the case of acetate anion, we can draw two resonance structures. Correct. Therefore, acetate, this is the conjugate base of acetic acid here. Two resonance structures are possible here. Now the hybrid will be so there will be a partial double bond here, which we can show with the dashes like this. Now there will be a partial negative charge on the oxygen here. That is the negative charge on the oxygen. Okay, it is delocalized here over the two oxygen atoms here. Okay, now the carboxylate anion here, the resonance structure, it is stabilized. Conjugate base is stabilized because the negative charge, it is delocalized on two oxygen atoms here. Okay, the position of the pi bond is different. So this is the hybrid here, and the position of the pi bond is different, and the lone pair, it is also different here. Hybrid. This is the hybrid structure here. Okay, the resonance structure is a hybrid structure. So the carboxylate anion, it will have less attraction for a proton because the negative charge, it is delocalized here. Okay, delocalization of the negative charge, because of that thing, the conjugate base becomes weak here. Delocalization of the electrons density, it will stabilize the acetate anion here, making it a weaker base. Correct. Now the resonance delocalization makes acetate more stable. More stable means weaker. Correct. A weaker base here. Okay, than the ethoxide anion. Ethoxide, there is no delocalization, and the negative charge, it is localized on that oxygen atom here. Therefore, acetic acid, it is a stronger acid compared to ethanol here. Okay, this is a general principle here. Because the resonance stabilization of the conjugate base, we are concerned with that. Therefore, the acidity of the acid HA, acidity of the acid HA, it increases when the conjugate base A minus, this is our conjugate base here, it is resonance stabilized here. Resonance stabilization means is a delocalization of the electrons. The electron, the negative charge is spread over two oxygen atoms here. Therefore, the conjugate base has become weak. As a result, the static acid, acetic acid is a strong acid here. Now let us compare with the phenol. That is, phenol we have, which is the conjugate base here. Phenol will give you phenoxide anion. So now let us compare the relative stabilities of the conjugate bases, the phenoxide, acetate, ethoxide, and all this kind of a thing, and see which is more stabilized one and which is more weaker. Therefore, we can say the relative acidity of the static material. Okay, so phenol is giving phenoxide anion. Now we have to compare the acidity. Let us see the acidity factor of the phenoxide anion here. That is, this is our phenol. So this is phenol. So the conjugate base of phenol will be the phenoxide anion. Correct. This is the conjugate base. This is the phenoxide anion here. So now let us see the resonance stabilization of the phenoxide anion, in what way the electron pairs are moving here. Okay, now this lone pair here, it will go like this. Then here the pi electrons, it goes like this here. Okay, this is our structure 1. This is structure 1. Then the second structure will be okay. So here there will be double bond now. Okay, now here there is a negative charge. This double bond intact and this double bond intact here. Now what happens? These electrons migration here, correct, like this. Okay, this is our structure 2. Structure 2. Then here we will be getting another structure. Third structure. So in the third structure, there is a double bond here. Okay, now this double bond is intact. There is a negative charge here. There is a negative charge here. Okay, so now how the electrons will be migrating further? Here, this electrons here, it will go like this. Then this correct. This is structure 3. Now structure 4 will be negative charge here. Okay, this is structure 4. Then next structure here, this electron will migrate here, correct. This will go like this, this will go like this. Then we get the 5th resonance structure here. Okay, this is structure number 5 here. Okay, now the resonance hybrid will be something like this. We can draw. That is, there will be a dashed lines we can draw. No, sorry. Oxygen. Then this electron densities delocalization we can show like this. Okay, now here there will be a partial negative charge, correct. There will be a partial negative charge here, there will be a partial negative charge here, there will be a partial negative charge here, correct. Now in this oxygen, partial double bond character we can show here, correct. Therefore there will be a partial negative charge here also here. So this is the hybrid of the phenoxide anion, correct. Therefore the phenoxide anion, the stability we'll have to see now, correct. So the hybrid will be resonance stabilized here. Therefore we have 5 structures here we have drawn here, that the conjugate base of phenol, that is phenoxide anion, the structures, there will be the negative charge is dispersed over a total of 4 different atoms here now. Okay, here the phenoxide, it is more stable than ethoxide. Okay, but it is less stable than acetate, because the reason here will be acetate has got 2 electronegative oxygen atoms there. In the case of acetate, we have seen the conjugate base acetate, it is stabilized by the delocalization of the negative charge over 2 oxygen atoms there. Correct. But in the case of phenoxide here, there is only one oxygen. Correct. Acetate has got two electronegative oxygen atoms. On those two electronegative oxygen atoms, the electron density is delocalized here. But here, the negative charge in the case of phenoxide anion, this is the phenoxide anion here. The negative charge, it is dispersed or rather delocalized only on one oxygen atom. Correct. So, the phenoxide is more stable compared to ethoxide here, because ethoxide there is no resonance stabilization at all. That is, the negative charge is localized under the oxygen atom here. Okay, therefore, and less the acetate anion, the negative charge is delocalized on two oxygen atoms here. And in the case of phenoxide anion, or only one oxygen atom here, negative charge. Delocalization only on only one oxygen is there here. Okay, therefore phenoxide has got only one oxygen. Therefore phenoxide anion, it is more stable than ethoxide and less stable than acetate here. That is stability. If you see the stability of phenoxide, that is phenoxide is more stable than ethoxide. Stability of phenoxide, it is greater than ethoxide. Correct. But less stable than acetate. Phenoxide, it is less stable than acetate. Correct. Therefore, acetate anion, that is the most stable one here, resonance stabilized here, because of the presence of two electronegative oxygen atoms on which the negative charge is delocalized. Correct. Now, here, and because of that, acetic acid is the strongest acid of the three here. Correct. Now, here in the case of phenoxide, there are other 2 points which we'll have to see here. In the case of phenoxide, if you examine the structures here, structure 1, 2, 3, 4, 5, we can see structure 2 and structure 3 and structure 4. There is a negative charge over the carbon atoms here. Okay, therefore this is a less stable one, because the negative charge over carbon is a less electronegative atom, negative charge over carbon atom. Okay, therefore the structure 2, 3 and 4, they are less stable than structures 1 and 5 here, which have the negative charge on oxygen. Okay, oxygen is more electronegative compared to carbon atom here. Therefore, a negative charge on the carbon atom, the structure becomes unstable here. Therefore, in the resonance hybrid, if you see, structures 2, 3 and 4, they are minor contributors here. Correct. That is, resonance structures 1 and 5 have intact aromatic structure here. Aromatic rings are there. Okay. But in the case of structures 2 to 4, 2, 3 and 4, they do not have it. Therefore, 2, 3 and 4, they are less stable compared to 1 and 5 here. Now, if you see the contribution aspect of it, you see the major contributor and minor contributor. We have seen in the case of resonance hybrid that which structures will be a major contributor here. That is, structures 1 and 5 will be a major contributor, and 2, 3 and 4 will be minor contributors here. Okay, resonance stabilization accounts for why carboxylic acids are more acidic than other compounds with OH bonds, namely alcohols and phenols here. Okay. Now, let us examine the points here. That is, we have seen that 2, 3, 4, they are minor contributors, okay, to the resonance hybrid because of the higher energy here. Now, 1 and 5 are major contributors here because of the OH bond here. This RCOH, because this R compound RCOH, that is a carboxylic acid here. Then we have ROH, that is an alcohol. Then we have C6H5OH phenol. All these compounds are acidic compounds, more acidic compared to most other organic compounds there. Correct. Therefore, a carboxylic acid, it is a stronger acid compared to an alcohol, okay, or a phenol, because conjugate base is more, that most effectively stabilized, resonance stabilized. Correct. So now, let us examine the case with bases. The basicity. What is meant by basicity? Let us see here. So different, now we have seen how will you see the different relative basicities of different compounds here. Now we have seen the relative acidities we can compare, of the different the relative acidities of different compounds we can compare using their pKa values here. Correct. In the same way, the relative basicities, okay, of different compounds we can compare using the pKa values of their conjugate acids here. Correct. Now, one of the most important basic compound, it is an amine. Amines, So what are these amines here? Now, before that, let us see the bases. Now, the strong acids, they have weak bases now. Correct. We know the strong acids have weak conjugate bases and weak acids have strong conjugate bases here. So just like acids, even in bases, we have strong bases and weak bases here. Okay, they are classified as strong bases and weak bases here. Now, the relative acidity that we have seen now, using pKa values, we can compare here. So, in the case of bases, the relative basicity we will be comparing using the pKa values of the conjugate acids there. Okay. Now, weak bases, they are stable species. You know that. They do not readily share their electrons to form bonds with protons there. Now, strong bases, okay, they want to share their electrons to form bonds with protons there. Now, strong acids, it will give weak conjugate bases here. Okay. Now, the more stable the conjugate base. Okay. Now, then in that case, what happens? The equilibrium, it will be shifted towards that conjugate base here. Correct. So, this is fundamental things about bases here. Now, let us see about amines. Okay. The amine compounds, this is the chemistry of amines, it is determined by the availability of a lone pair of electrons here. Now, how will you compare the relative basicity? It all depends upon the availability of the lone pair of electrons there. So, any factor that increases the basicity, that is the availability of the lone pair of electrons there, or non-bonding pair of electrons, so that will increase the basicity here. So, now here the most important thing is the chemistry of amines. Okay, amines, it is determined by the lone pair of electrons on the nitrogen atom here. Amines are actually, they are derivatives of ammonia. Okay, from ammonia it has come. This molecule ammonia replacing hydrogen with say an alkyl group here. Okay, we get an amine here. Alkyl, an amine, methylamine, ethylamine, and all this kind of thing. In the same way, we can replace, say, two hydrogens. Then we get an R2NH here. We can replace it with a phenyl group here. The aryl amine we get. That is aniline. Like this. These amines are derivatives of ammonia. Okay. So, by replacing one or more of hydrogen atoms by alkyl or aryl groups here. Okay. Now, they are strong bases. Amines are strong bases here. Okay. And not only bases, they are better nucleophiles also. Bases and nucleophiles. Amines are strong bases and they are better nucleophiles also. Okay, they are organic nitrogen compounds here. Okay, now so the nitrogen atom here. Nitrogen atom has got a non-bonded electron pair. Okay, making it a base and a nucleophile because of the lone pair of electron on the nitrogen atom. This is the most important thing here. Lone pair on nitrogen. Okay, this will make it as a base. A base means it will react with a proton. Okay, so in the Bronsted acid here, so it will form NH plus here. Correct? Plus A minus. So, like this we will be getting it. A compound here. This is actually, reaction as a base here. In the case of amine, reacting with a Bronsted acid. And in the case of, amine, it can react as a nucleophile with an electrophilic site here. That is E, electrophilic site. So what will happen here? The charge will go like this. So this lone pair will take this electrophile here. This is reaction as a nucleophile. Amines are reacting with an electrophilic site here. Okay, so we will be getting a ammonium compound kind of a thing. Okay, here it will be the electrophile bonding, then plus, then we have X minus here. This is an ammonium salt. Okay, so ammonium salt here. Correct. So amines can the reactions of amine, it is as a base here. Okay, base means as a result, amines will react with the electrophiles also. It will react as a nucleophile here to form ammonium salts here. Okay, now in the periodic table, if you see, these only 3 elements are there. Okay, in the second row of the periodic table, we can say that have non-bonded electron pairs or lone pairs of electrons here. That is nitrogen, oxygen, fluorine. These are the 3 elements in the second row of the periodic table having a lone pair of electrons or a non-bonding pair of electrons here. Now basicity and nucleophilicity. Okay, it decreases across a row of the periodic table. Now we have seen the acidity. Acidity increases across a row of the periodic table from left to right. In the same way, basicity, okay, the basicity and nucleophilicity here, it decreases across the row of a periodic table. Nitrogen, it is the most basic one here. Okay, nitrogen, most basic, and fluorine, least basic. Okay, when we are moving from the periodic table here, left to right of the periodic table, when you are going there, that is nitrogen is the most basic and most nucleophilic. Most basic, not only basic, but nucleophilic also here. Correct. Most basic and most nucleophilic of the elements here in the second row of the periodic table here. Correct. That is something basic factor about amines here. Now let us compare the amine, the basicity of amines, alkyl amine and aryl amine. Now because the electron delocalization, again, briefly I will explain to you alkyl amines and aryl amines here. Alkyl amines means is just like say RNH2, a compound of this nature, that is CH3, say CH2, NH2. That is the ethylamine here. Okay, this is ethylamine, and there is a aryl amines here. Alkyl group, aryl group. Aryl amine will be C6H5 NH2. This is our aniline. Okay, now let us see the relative basicity. Okay, just like the phenol, we have seen the relative acidity here. Now here, see the basicity. Now the basicity, what is the deciding factor? It is the availability of the non-bonded electron pair on the nitrogen atom here. So in the case of a nitrogen, organic nitrogen compounds, or here the amine compounds here, the basicity deciding factor. Okay, the deciding factor for basicity, it is the availability of the non-bonded electron pair, that is the lone pair of electrons. Therefore, the ethylamine, if you see the electron pair, it is localized on the nitrogen atom here. So this is our ethylamine. There is a localization. This electron pair is localized on this nitrogen atom here. Okay, but in the case of aniline, that is the aryl amine here, we can see the electron delocalization is there in the case of aniline. Okay, so roughly I will just draw it for you. This is our aniline here. So how these electrons are shifting here, I will just draw it neatly. Okay. This is a lone pair of electrons here. Now, this is our structure 1. This lone pair, it will come like this. Then, okay, this is our structure 1. Now, another delocalization, resonance delocalization we can see is exactly like a phenol only. Okay. NH2 plus. Now here, this electron pair, it will go. Okay. So the third structure will be so here there will be a negative charge. Correct. So this is our third structure. So here, this pi electron movement here. Correct. Then this. Okay. So the fourth structure will be this is our fourth structure here. Here this electron pair, it will come like this. Then it will go like this here. Okay. So we'll be finally getting aniline here. Correct. Now, this is the way the electron delocalization takes place in the case of an aryl amine, that is aniline here. And this kind of delocalization, it is not there in the case of ethylamine here. Okay, therefore, the base because the basicity deciding factor, it is the availability of the non-bonded electron pair on the nitrogen atom here. Correct. So, in the case of ethylamine, the electron pair is localized. In arylamine, that is the case of aniline, the electron pair is delocalized over the benzene ring here. Okay, this decreases the electron density on the nitrogen atom. Okay, and therefore aniline is less basic than ethylamine. Correct? So electron pair is localized on the nitrogen atom means the electron density is more, the basicity is more there, because the electrons are readily available for forming bond with a proton there. Correct? Therefore, in the case of ethylamine, the basicity, we are not talking about acidity here, the basicity of ethylamine, because it depends upon the electron pair, availability of the electron pair on the nitrogen atom here. In the case of ethylamine, the lone pair of electrons, it is stabilized, rather it is localized on the nitrogen atoms here. Electron pair is localized on the nitrogen atom. But in the case of aniline, what happens? These electron pair, correct? The electron pair is delocalized on the benzene ring here. Okay. Therefore, this decreases the electron density on the nitrogen atom here. Therefore, aniline becomes less basic than ethylamine. Aniline less basic than ethylamine. Correct. That is, alkyl amine is more basic. because there is no electron delocalization here in the case of an alkyl amine here. Okay, localized electron pair there. Now the pKa value, if you see, CH3 aniline is less basic than ethylamine. Now let us see the pKa values here. The pKa values of CH3, CH2, then NH3 plus. This is the conjugate acid of the base there, ethylamine here. Okay, so this pKa value of this conjugate acid, it is higher than the pKa value of C6H5NH3 plus of the aniline here. Okay, pKa value is higher in the case of this conjugate acid. Therefore, there is a weaker acid here. Weaker acid means stronger base. Stronger base will give a weaker conjugate base. Correct. So, pKa here, in the case of ethylamine, it is higher. Okay. So, compared to the pKa value of C6H5NH3 plus, that is a conjugate acid of this aniline here. NH3 plus, that is a conjugate acid of aniline. Therefore, ethylamine, it is a stronger base compared to aniline here. So, aryl amines, they are less basic. Aryl amines are less basic than alkyl amines here, because the electron pair on the nitrogen atom, it is delocalized. Correct. Because of the delocalization of the electron pair, the basicity decreases. Now here, if you see substituted anilines here, okay, substituted aniline, that means we have, this is our aniline. Okay, we have a group here. There is a group, say, substitution can be either a electron donating group or it can be electron withdrawing group. So what will be the nature of the acidity here? So this is withdrawing group here, electron W. So D, that is electron donating groups here, that is be NH2. So electron donating, it can be an OH group or it can be a OR group, ether group, then we can have a alkyl group and all. Here in the case of W, that is electron withdrawing groups, there are plenty. One is our halogen groups, then we have the aldehyde, then we have the ether, carbonyl group, then COOR group, COH group. There are so many groups like this, they are all electron withdrawing groups, cyanide groups and all this kind of a thing. Therefore, two different types of substituents are possible here. In the case of aniline, on the benzene ring, we can have two different types of substituents. Okay, one will be an electron donating kind of a substituent and another will be an electron withdrawing kind of a substituent. So, in the case of an electron donating, electron donor groups, because they will add electron density to the benzene ring here. Okay, therefore, aryl amine, it will become more basic than aniline here. That means an amine with a substituent electron donating group. Okay, it will make the benzene ring, it will become more basic compared to aniline. Therefore, an basicity, it will depend upon the nature of the substituent here. So, electron donor groups, it will add electron density. Therefore, the electron density of the benzene ring will be increased, making aryl amine more basic than aniline here. In the case of an electron donating group here. So, but in the case of the electron withdrawing group, what will happen? Electron density is withdrawn. Once the electron density is withdrawn from the benzene ring, means aryl amine becomes less basic here. So, here it will be more basic and here it will be less basic. Electron withdrawing groups here. Okay, there will be two different types of substituent groups here we can identify. Correct? Electron donating groups and electron withdrawing groups. Electron withdrawing groups remove the electron density from the benzene ring. Therefore, aryl amine, it becomes less basic than aniline. But in the case of electron donating groups, what happens? That is, electron density is added to the benzene ring, making it more basic. Okay. So, thank you very much for listening.